just to make sure you see the whole picture. So have you heard something about abelian categories? Yeah? No? So essentially what we need to know is just some derived functors of Hom, so cohomology. Maybe I should write cohomology of well, finite. We will deal with finite or profinite groups. Profinite groups. But actually, we will deal with certain abelian categories. So an abelian category. This means that we have abelian group structures on morphisms of this on the objects of this category. And we have a notion of kernel, co-kernel, and everything is good. So as a first approximation, you can think of categories of modules. So modules of a ring, or actually when we deal with not necessarily finite groups, but with certain topological groups of profinite, and then we actually work with not with all modules, but sometimes with smooth modules, smooth modules of profinite groups. And smooth means that the stabilizers are open. Stabilizers of all elements of these modules in the groups are open. Okay, and now we actually, as I said, we're interested in cohomology, but the way to define them is to define them as certain derived functors of the functor Hom.
Excuse me, stabilizers of which action?
So you see that what is a module over a group? It is a certain abelian group. So it is an abelian group where some group G acts, and you can consider all elements of this abelian group.
Grouping model. Is it? No.
Yes, it is a module over the group ring, but when we say that module is smooth, this means that this stabilizer as a subgroup of G. Okay, so so now given we have actually so assume that X some object of an object, and to each object we can associate two functors. The first one is morphisms from this functor, from this object. This is a functor from A to, say, abelian groups. And another one is the functor of morphisms to this again from more or less the same category, but this functor is contravariant. So you can consider this as a functor from the opposite category, again to the category of abelian groups. And you can show that these functors are, sorry?
What's an opposite category?
It is the same category with the same objects, but the arrows are reversed. Okay, so and so these functors are what are called they are left exact. They are left exact. This means that if we have a short exact sequence, so if so ABC is exact in the sense that the kernel of the next arrow coincides with the image of the previous arrow. So, for instance, this is injective and this is surjective, and the kernel of this arrow coincides with the image of this one. Then so let's call this F. Then 0 F of A. Yeah, maybe. Yeah, maybe I should. Yes, maybe it's not a good idea. Maybe it's not even a good idea to write this way because. Yeah, maybe I should state this in more in more precise terms. So yeah, so then home from so if we consider morphisms from X, then this functor preserves exactness on the left. Yes, so it is indeed left exact from X B X, so is exact. But you see that it is exact, but we don't claim that the last arrow is surjective. And similarly, we claim that this.
What does it mean that this chain is exact?
So this one, a sequence is exact if the kernel of the next arrow coincides with the image of the previous arrow. For instance, we
So this is the kernel of the map of regions.
yeah. So let's call it alpha beta. So we claim that beta is surjective here, and the kernel of beta is the image of alpha. Yeah, so maybe these are left exact. Okay, so more concretely, yeah. So this and concerning the functor of morphisms to X, we claim that yeah. So again, 0 goes to from C to X is embedded into home from B to X, and goes to come from A to X. So they are exact. So they are exact, but we do not claim that the last arrows are surjective. There is a notion of derived functors. So this notion is very general. So, but we will use it only for these two functors. So namely, there is a way to extend this sequence to make it exact and to make it continue. Then there exist functors that are called x with certain number that make this sequence continue until infinity, if you wish. But actually, you see that so far we have two distinct sequences. So in principle, you could say that we should have two sequences of functors. Mm-hmm. So where, say, x is placed here and x is placed in the first as the origin of our morphisms. But the funny thing is that actually they coincide in the sense that that if we apply I don't know how to maybe I should put here 1 and 2 and the claim is that these functors coincide like for our original functors. So this you can consider this as x number 0. So this will be x1 and this will be this will be x2 and this will be x1. And the claim is that actually these two functors coincide. Well, I'm not. You see, this is just a brief, very brief overview of something which we will not actually use this very hard, but it is useful to know that such a picture exists. Yeah, and as a general reference, you can find any book, but for instance, by Weibel. This is an introduction to homological algebra. Something like this, or something else, maybe.
Backwards, do you mean that they naturally is an isomorphic?
Yes, yes, yes. Okay. And there are some very explicit descriptions. So there is a description explaining the notation. Yeah. So ext means extensions. So for instance, x1 of x and y, you can think of this as a set of isomorphism classes of extensions of so extensions means that you consider short exact sequences like this. Sorry, 0. Okay. So modulo isomorphisms. So modulo isomorphisms means that you identify two extensions admitting morphisms between them. So if there is a morphism making this diagram, then they are equivalent. Oh, isomorphic. Okay, yeah, so now so how do we use these techniques? We will deal with certain short exact sequences of modules like this, and we will use certain x. Yeah, so let me give an example. So basically we have only one example, so we can always consider the categories of smooth modules of this one. This one's smooth modules over profiling groups. That's the only category we consider. And so example. So G profiling group, and Z is the trivial G module. So trivial G module, and then morphisms. Let us try to see what are the morphisms. Maybe let me denote this by G. So denote by home G the morphisms. The morphisms in the category of smooth G modules of smooth.
Excuse me, what do you mean by trivial G model? Text just like a...
Yeah, trivial means that the G action is trivial. So G acts identically. So with the identical action, G action. Okay, so so you may ask what are the morphisms from this module. So what is this? And of course Z means the integers. So as an abelian group, this is the group, the infinite abelian group, infinite cyclic group. So the question is, how could you describe the morphisms from this trivial G module? Now, you see that we want them to be compatible with the G action. So these are modules. These are G modules. Yeah. So there is a G action here. Well, it is trivial, but it is a G action, and there is a G action here. So and we want this to be compatible. Yeah. So we want.
So we can just look at cyclic submodulus of M on which G acts trivially, no?
Well, you see that it is sufficient any morphism from the cyclic group. Yeah, you just choose a generator, say 1, and then the morphism is determined by the image of this generator. Okay. So
if J acts trivially on M,
no, it need not. It need not be. It need not to act trivially.
and M small, I
M
mean.
is here.
Yeah.
So you mean if? Yes, you're right. So if you see that actually the G action is trivial here, so the generator is fixed, and it is sent to M. But this means that the image of the generator should be fixed. And therefore, actually, this simply means that you identify these morphisms with the fixed part of this module. Fixed. So the fixed part. Okay, and the and the extensions. So notation, or definition. Definition. The cohomology. The cohomology of G with coefficients and M are by definition the X groups of this trivial module and M. Yeah? So this well, this is you see that it's so far it's very abstract and formal, but maybe I could give you an explicit explicit description of this. For instance, we will deal mostly with H1, and maybe if we will have time, we will also discuss H2. But so far, we only need H1. So H1 of GM can be described as follows. It is the group of maps from G to M such that f of GH is equal to f of G to the sorry, f of G plus f of H to the G. And so these are called one cocycles. So one cocycles on G with coefficients in M. And there are those cocycles which are called coboundaries. Coboundaries, they are, so you consider the following functions which are of of the form G goes to Gm minus m. So for all elements of m. So let us check that this is indeed so this relation really holds. Yeah. So to make sure that this is correct. So what is this? So f of gh will be ghm minus m, and so the question is whether this coincides with gm minus m plus g of hm minus m. Yeah, it seems that it's okay. Yeah. So this is indeed a subgroup, and so you see that in some sense this is this reminds homomorphisms from G to M, and we will actually use this in practice. Namely, it is indeed the set of homomorphisms in the case when M is trivial, when the action of G on M is identical. Yeah, then this will be so then we can forget this G, this action, and on the other hand this will be 0. Yeah, if the G action is trivial. Okay, so this is H1. Now let me so yeah, I'm sorry, I have to make a correction. So this is correct if in the case when G is discrete, for instance. So this is for this is if G is finite, and in general. So this is in general, if G is profinite, if G is profinite, so it is a limit. So you can limit of what? Of certain finite finite groups, so you can think of this as a limit of quotients of G by finite normal subgroups. So n I, so they are normal and open normal subgroups. So here, so. Sorry?
This is part 2 and where's the
Part
part 1?
1, here in the case where, so here we assume that G is finite.
And I is finite in this.
Yes, that's right, yeah. Yeah, so they are open and therefore they are finite, yeah. Yeah, and in this case, we can show that this first x, well, actually it doesn't matter, does not really matter. What is this? Just you can put here any cohomology. So then this any cohomology coincides with the co-limit, of over this indices, and I of what? Of the cohomology of the quotient with coefficients in the fixed part of the module fixed by this open subgroup. Yeah. So in a sense, so this colimit means that you essentially you consider the union. Okay, but what is important here that actually we reduce everything to the case of finite groups. So even when we talk about profinite group, everything is reduced to the finite ones. Okay, now let me give you an example of such cohomology. So you can use this as a definition actually. And the only so we have so far we only use H1, so you can use this definition. But we want to have exact sequences, of course. So and the exact sequences will be used quite often. And one more remark. So one more remark is that we have defined these x functors as certain functors which make our sequences exact for well, making our long exact sequences. So there is one case where so what is important is the cases where these functors vanish, and these functors vanish when our original functor of morphism to x or from x was already exact. So if hom from x or is exact, then x with a higher x from x vanish. Yeah, and similarly for those x morphisms such that morphism to them is exact, then the same holds. Yeah, so then the higher x. Oh, sorry, vice versa. Okay, so in the case, you probably know that in the case of modules, such objects are called projective, and in the case of modules, again, such modules are called injective. So.
Excuse me, definition of x1. Do we have in the right hand side all extension classes or just one?
All.
Okay.
All. You see that so far it is just a set.
Mm-hmm.
That's maybe that's the problem you are asking. Yeah. So this is a set, but actually this set carries a natural structure of an abelian group. Maybe I should say this. So, for instance, if you have, suppose that you have two extensions.
Mm-hmm.
So, what could you do with this? How to define their sum?
put some in the middle and how should we reject?
Well, if we maybe I can erase this, yeah. So how could we define construct something which is related to both of them? Yeah. So, for instance, we can consider the direct sum. And then, so what could we do? We could.
Oh, we can put.
Yeah, we can consider y embedded diagonally, and then consider some quotient. Yeah. So, for instance, we could. Well, maybe it's not a good notation diagonally because so phi prime, phi prime, and then maybe we should mod out by something. For instance, we have here we have psi prime. We can consider the preimage of psi prime. Sorry. Well, we just have to play a little bit with diagonals and preimages of diagonals. So you can, you can consider the preimage, for instance, preimage of the diagonal of x. Yeah. So this is a map from the direct sum to the square of x. Yeah. So you can consider the preimage of the diagonal of x in the square, and mod out by something like so this is x, and this is yeah. So here you this is this coincides, and yeah, and mod out by some maybe anti-diagonal embedding. Yeah, something like phi, maybe even well, something, maybe some image of y. So you see that here you have some two copies of y. So you just have to make appropriate. Maybe I'm wrong. Just try to play a little bit, and yeah, and to get so this is an addition, and to make
Subtraction.
no subtraction. It's not the problem. The problem is to make it linear. Yeah. So you have to be able to multiply by the elements of the ring, and this is done by changing, well, either phi or psi. You just compose this with certain yeah. For instance, if this over a field, you just compose this with multiplication. Yeah. So you can you have multiplication here, for instance, and you.
And from the right hand side, multiplication by the inverse of it, maybe to hold exactness.
from the right. Which one?
I mean, if we multiply phi by j, by sine of j, we should we modify somehow psi? No, we shouldn't. Okay.
No, it's if it is invertible, then there is no problem. Okay. Yeah, but I mean, it's of course in real life you never use this description because it's quite complicated. Because in principle you can define this the same way you can define higher extensions, but you just have to put here more arrows in the middle. But the problem is to define equivalences. So it's a bit complicated, and of course you never use this. But anyway, yeah. So this is so what is important for us that this is there are no extensions from projective. So this is projective objects, and these are injective. So if x is injective, then there are no high extensions with x. Okay, and now let me give an example. Actually, we have already told about the first cohomology, but we just didn't mention that this is a first, or at least a cocycle. Yeah. So, so example. We use this in Kummer theory. So how could we? So we assume that L over K is a Galois extension. With group G, and we have constructed abelian extensions in L of K using certain subgroups. So let me recall you that subgroups of K intersected with the nth powers modulo nth powers of elements of K. They correspond to abelian extensions of L in K. Yeah?
Groups of what?
Of K star, so it's well, you can omit some star, but just those we consider elements of K modulo nth powers of elements of K, but actually we consider only elements that have nth root in L. Yeah, because well, in principle, of course, you can pass to the to some separable closure or something like this. Yeah, and so let me explain how to get this from certain cohomology and how to interpret one cohomology group which had already appeared without mentioning cohomology or cocycles. So we can consider, so let mu n, so sorry, we have assumed, and so and K contains a primitive nth root of 1 of unity. So mu n, these are nth roots of unity. And so we have the following exact sequence. Mu n is embedded into the multiplicative group of of L, and it is mapped by raising to the nth powers to the group of all nth powers. And we can look at the cohomology of this of the group G. So and maybe I should state so as we saw here, morphisms from the trivial Z modules are just invariants in the fixed part of the module, and we denote such morphisms by H naught. Yeah, so H naught is just morphisms from. So let me write the exact sequence of the cohomology. So H naught of G nu n, H naught of G L star, H naught of G L n, H1 of G nu n, H1 of G L star. Okay, so so what's written here? So here we see only those nth roots of unity that are fixed by G, but they are all fixed by our assumption. They are all fixed by the group G. So now here, this is a Galois extension. So the fixed elements of G in L star is just the whole multiplicative group of K. And here we see that the fixed group is just the fixed group is just those nth powers of elements of L that are fixed by G, that belong to the field K.
How do you get this exact sequence?
We just raise
I mean
by raising to the nth power.
I mean the sequence of homologies.
Ah, this one.
Yes.
For any
Somehow we're using snake lemma.
no, you see that the point is that I haven't really defined the derived functors. So, but I just claim that there is a collection of functors that are called X with X1 and X2 and so on. But in our case, X1, X2 and so on, they are denoted by H. This means that we take X from the trivial G module Z, the integers. So we just apply these functors to. You see that so far we haven't defined this explicitly.
One more thing. Should we have an G model on the right? Okay, it is. Okay. And so the X functor continues our sequence infinitely.
Yes.
Okay.
Yes. So we have zeroth functors, then the first functors, then the second, and so on. Yeah. So so here we have those nth powers that are fixed by G. That is those that are in K. And here again the G action on the roots of unity is on nth roots of unity is trivial, and as we have discussed here, this means that the first cohomology is just the homomorphisms. So these are just homomorphisms from G to mu n. And so the question, what is this? And this is actually, so what, let us look at this definition. Well, it's not, well, you can think of this as a definition, of course, but because we don't have any other. So, yeah, so I claim that H1 of G, so H1 of G L star, and these are isomorphism classes of semilinear representations of G. Isomorphism classes is of semilinear representations of G over L of dimension 1 of rank 1. And as an operation, you can tensor them. Yeah, you have tensor multiplication. So how to see this? Or we can start with 1 cocycles. So what are 1 cocycle? What is a 1 cocycle? So let us let A G be a 1 cocycle. So how could you define this this representation? You just so you fix some. So here E is just a basis element. So this is just a non-zero vector, and you have to define the action of the group. So G. So let's try to just multiply by this element by AG. Yeah. So we just have to check that this really gives an action. Yeah. So then, so for all G and G, we have to check that what is G H E. Yeah. So what would be, so from what is this? Well, from one point of view, this is, if you think of this as a single element, then this should be AGH times E, and on the other hand, this is G applied to HE. Yeah, so this is AH times E, and this is AH to which applied G times GE, and GE is AG times E. Yeah. So, and we see that this is what we want, yeah, because this is exactly our relation, so it's okay. So we have constructed a certain semilinear representation with a given with a fixed generator, yeah, and if you think of coboundaries reflect possible choices of bases. You can replace E. You can replace E by some F times E. Yeah, and what you get will be changed by such a multiple. You see that here we write this additively, but the only difference is that here our we write everything multiplicatively. Okay, and well, and vice versa. So if we have a semilinear representation, then we can choose a basis, and then so if L a semilinear representation, we fix some element in this L, and then we can define one cocycle by this condition, and of course this is a bijection. Okay, and we know that all semilinear representations of finite groups are trivial, so this means that this is 0. And what does this mean? This means that homomorphisms from our Galois group to the roots of unity and roots of unity is precisely the co-kernel of this map. So and this map is raising to the nth power, and so this gives this gives an isomorphism. Yeah. So. Okay. So and this gives us an isomorphism K star intersected with nth powers in L, modular nth powers of K, and just isomorphic to the group of homomorphisms from G to N. And what does this mean? This means that the subgroups. So we are interested in those. Yeah. So. I'm sorry. Subgroups abelian. I forgot an extra condition. Abelian extensions of L in K of period n. This means that the Galois group is annihilated by multiplication by n. Okay, and yeah, so all such groups, so all such Galois groups, so yeah, maybe Galois groups. Maybe I should extensions. Let me call them F. So F is determined by its Galois group, by the Galois group of L over F, and this group actually is the kernel. Is the common kernel of certain phi I. Phi I is a homomorphism from G to N, and that's how we get. So, and of course, it is easy to construct. Each such homomorphism comes from an element here. So it's you just take an element A and send it to the homomorphism, which sends an element of the group to the quotient, to the following quotient. And well, I'm just rewriting. You see that we have already discussed this, but without mentioning cohomology. But what I'm going to do right now, I want to mm, to state another vanishing. So you see, so far we know only vanishing of the first cohomology of the multiplicative group, and sometimes it is called Hilbert's theorem 90. But what I'm going to say is another vanishing. Sometimes it is called the additive theorem 90, but it's more in a sense it's a little bit misleading because this result is more general. So the claim is that proposition is that the cohomology, all cohomologies, we are interested only in the first one, but actually it's true for all cohomology of the additive group. It is 0. And the reason for that is the following. So what is it is, let us discuss what is called Shapiro's lemma. So, well, Shapiro's lemma, it deals with the following. Again, we will need only some particular case where this with group cohomology. So let H be a subgroup of G. M an H module. Next we denote by induction from G to H M the following set of maps H equivalent maps from G to M. You see that maybe I should write just to make sure that we understand what's going on. Left. So we have the set of maps, and this set of maps is itself a G module. Yeah. So let F be a map from. What does it mean that they are H equivariant? So H equivariant. This means that the H action commutes with this map. So F of HG is equal to F of GH for all elements of the subgroup. Okay, and now we have also the G action on this. Well, and of course the maps you can add. Yeah, so it is an abelian group, but we have to define the. So by definition, so if F is a map from G to M, then the group acts on these maps as follows. You can pose that G of X applied to F is just the F calculated on X times G. So So this is by definition. Okay. And then the claim is that, so this is the induced module. And then the cohomology of the induced module coincide with the cohomology of original module. Cohomology of M. Okay. Yeah. So actually, so modulo some formalities. The proof is trivial. So if I mean formalities, I mean the construction of derived functors. So modulo this construction of derived functors, you just have to check that this holds for the zeros cohomology. So that we just have to check that the functor. So you see that these are just extensions from SG modules from something. Doesn't really matter, from in our case Z to something. And similarly here. So what we have to check is that morphisms to the induced module H, G, M are the same as the morphisms from as H modules from something to M. Yeah, and actually this is quite well. This is a direct so some direct check. And yeah, and now how to deduce this proposition from Shapiro's lemma? Okay, yeah, so by normal basis theorem, this L as a G module is isomorphic to the group ring of the group G, yeah, and this is precisely what is this group ring? This is precisely the module of maps from G to K, and this is the trivial yeah, from yeah, sorry. And that's it, because so this is, well, this is just induced representation. So this is induced representation of the trivial group extended to G. Yeah, and therefore the cohomology of L of G with coefficients in L are isomorphic to the cohomology of the trivial group with coefficients in K. So this is 0. Okay. Now, so we have, you see that in Kummer theory we have constructed all abelian extensions of period prime to characteristic, yeah, assuming that we have appropriate roots of unity. But now we are able to construct say cyclic extensions of degree equal to not only cyclic but also all abelian extensions of period equal to the characteristic. So this is Artin-Schreier theory. Artin-Schreier theory. Maybe Artin-Schreier Witt. Oh. So the idea is as before. So in the case of Kummer theory, we used roots of unity, and we yeah, we can try to do something like this. Yeah, but for instance, let us start with Artin-Schreier. Artin-Schreier. So we can consider so P is the characteristic of our field L. So G is the Galois group, well, some a finite group of automorphisms. Of L, and K is the fixed field. Yeah, so we can consider the following sequence. This prime field. This is it is positive. Yeah? The prime field is embedded into L, and then we can map L into itself somehow. Yeah. Let us call this P of L. For instance, we can send each element of L to x to the p minus x. And then the kernel will be precisely the prime subfield. And let's look at the long exact sequence of cohomology. Yeah, maybe I should state, yeah, maybe before explaining the proof, I should state the claim. Yeah, the claim is that there is one-to-one correspondence between subgroups of what? Of P of L intersected with K modulo P of K and extensions abelian extensions of K and L, extensions of K and L of period P. Yeah, namely to each subgroup here, to each subgroup H, you associate the subfield generated by the preimage of H preimage under this map P. And yeah, and this is bijective. Yeah, so so the proof is easy, modulo everything we have mentioned before. So the proof, you just take the cohomology of the group G with coefficients in these three modules. So what you get? So you get the following exact sequence. So Fp of course is fixed. L invariance of L is K. Then it is mapped by P to the intersection of K and P of L. Next map is to the first cohomology of G with coefficients in Fp. And finally, it's mapped to the first cohomology of G with coefficients in L. So the first cohomology of G with coefficients in Fp is just a homomorphism group from G to Fp. And as we just saw here, the last group is 0. And this, so this gives us an isomorphism, this one. So this will be K intersected with P of L, modulo P of K is isomorphic to the dual group of the group of homomorphisms from G to Fp. And then the argument will be the same as in the case of Kummer theorem, because we just well, you see that any yeah, it's like the same argument as here. In the case of Kummer theory, there is no difference. Yeah. So that's how you get abelian extensions of period equal to the characteristic. And you may ask how to construct abelian extensions of period say p square. And that's why Vit appears here. So what do we want? We want more or less the same sequence as here, but instead of Z mod, so let me put here Z mod P. Instead of Z mod P, we want to put here Z mod P square. And how to do this? Well, in principle, you actually this theory is due to Witt, and that's where his Witt vectors appear. But actually, I'm not going to discuss Witt vectors right now. So let me just say that what could we how could we get this type of sequence? So without, well, actually it is close. It is very close to Witt vectors, but it is more rough. Yeah. So than Witt vectors. So what could we do? We could look at the ring of formal series over L. So we can consider those formal series over. So what do we have? Well, x, yeah. Sorry. 1 plus x L. Well, not formal series, but truncated polynomials. Yeah. So we consider truncated polynomials. So truncated? Что? Обрезанные. Modulo x to the n. So this is an abelian. Well, it's so we consider this as a multiplicative group. Yeah. So this is multiplicative group. So it is a G module. And what do we want? We want to find some map with the kernel whose kernel is again the subgroup of truncated polynomials, but over the prime subfield. Yeah. So this will be 1 plus x f p of x modulo x to the n. Yeah, maybe I should put here 1. Yeah, so let me call this again p. So what would be p? P should send the f of x to what? To well, we just we can apply Frobenius to each coefficient here and divide by the same polynomial. Yeah, Frobenius of x over f of x. Well, let us call this m. So this will be p of m. Okay. So the question is, yeah. So now we just want to write down the long exact sequence of the cohomology, of the Galois cohomology. So what will be here? So here this is a trivial G module. Yeah, there is no action here. So by the way, what is this? So what is this group? You see that this is, well, for instance, you have an element x, 1 plus x. Yeah. So what can you do with this element? Yeah, maybe. Well, maybe it's not a good. It was not a good idea to write this way because. Yeah, because maybe we get more we get actually some trash here. Yes, I mean not only what we want, but I'm just trying to explain the idea. So, but it should not really be applied this way. Yeah. So actually, we should to make this work, we have to put here not n but then p to the n and then take some part of it. Yeah, so just. But anyway, this is you see that this is a finite abelian group. So you can play a little bit with this group to make it more like we want, namely well, you see that, for instance, if you try to raise this element to the various powers, yeah, what will you see? You will see that this element to the p to the n is equals to 1, yeah? But all smaller powers are non-zero, yeah, because the highest term, this degree is lower than x to the p to the n. So at least z mod p to the n embeds into this group f p x p to the n. Yeah. So at least we can get some information from. Let us call this, I don't know, maybe let's call this t. So so let us write the long exact sequence of cohomologies. So this will be this group T. Next M. What is M? M to the it will be just the same group, but with L replaced by K. And finally, it will be intersection. Well, maybe nothing special, just intersection with this group. And now H1 of T. So this H1 of T of G with coefficients in T. And now H1 of G with coefficients in M. Okay. So what is this? Is T is a trivial G model. So these are just homomorphisms. G to T. And finally, so you may ask, what is this? What is this group? And I claim that this is 0. For so this is 0, and the proof is quite obvious. Namely, let me state this more carefully. So the claim is that H, well, so lemma. So this cohomology of G with coefficients in 1 plus xl x modulo arbitrary power is 0, and the proof is by induction. Proof by induction on n. Well, if it is 1, then everything. Then this is clear. So in the case, yeah. So in the case, so how to pass from x n plus 1? We have the reduction x l x to the x n. And the kernel is, what is the kernel? The kernel is isomorphic to L. Namely, you send a to 1 plus x to the n a, yeah, this way. And now you just you see that, so this is cohomology HQ. So if Q is positive, then the cohomology of L is 0. So we have something, and the cohomology of this term is also 0. Yeah. Yeah, and so yeah, so we get that this vanishes. So this is 0, and therefore we get that homomorphisms from G to. So the conclusion is that homomorphisms from G to T are isomorphic to what? To 1 plus xl x modulo x to the p to the n intersected with the images of intersected with the p of m. Sorry. Invariance. We want invariance. So, yeah. So this is and modulo this map. Yeah, and this map is P. So modulo P of this. So modulo P of this x k x. X to the p to the n. Yeah, and so unfortunately we don't have time to correct this sequence, because you see that this is bigger than we want. So this is, of course, this is a finite group, but it is not cyclic. Yeah, but what we can do is yeah, so in principle we can distinguish certain part which are called width vectors, and then this will become indeed z mod p to the n, and then this group will be homomorphism to z to the p to the n, and then to obtain extensions with such group, we just consider the preimages of elements here, and that's how we construct extensions rather explicitly. Okay. Yeah, maybe I should stop here. Okay. Questions?